Good day, everyone. We'll be considering system classifications in this lecture. And recall that in our last, or say in our previous lecture, we described a system as the abstraction or an abstraction of anything that can take in an input and then operate on it, and afterwards generate an output. So in our last lecture, described a system to have an input, say X, fed into a system with a parameter K, and then it gives us an output where the output is the product of the scaling parameter and the input. So in other words, the output here is seen to be the mapping of X with K. So in other words, we say that the output of the system is represented by mapping the function K such that our Y, which is the output, is the same as SK. So the mapping function here, which is K, characterizes this system. Characterizes the system since it transforms X to Y. So if this is what the system does on a general scale, so what are the types of systems we have? So first, we'll talk about continuous time systems. So a continuous time system is a system that takes in a continuous time signal as the input and produces an output that is equally a continuous time signal. So we have S of t goes into the system. This is the system, and then produces an output Y of t. So in other words, both the input and the output are continuous time signals. Similar vein, the discrete time system is a system in which the input and the output are discrete time signals or sequences. So we have something like this. S of n goes into the system. Then we have I of n. Then we have static systems. Now, the static system is a memoryless system. Because the output depends on the present input, likely because the present output depends only on the present input. That is, given a system, say S of t, signal goes into the system, and then we have I of t. So the implication here is that Y of t is the same as S of t. So at t equal to 0, and y of 0 is the same as s of 0. And at t equal to 1, y of 1 is the same as s of 1. And at t equal to minus 1, then y of minus 1 is the same as s of minus 1. So at this point, it's worth mentioning that considering the time scale, let's say this is a time scale, we have 0, minus 1, minus 2, all the way to minus infinity. And here we have plus 1, plus 2, all the way to positive infinity. So from this scale, at point 0, we say we have the present time. And from 0 to infinity, we have the future. And from 0 to negative infinity, we have the past. Okay. So in other words, at the instant of time where we have probably at our present time, then we get the present input. So at the same instant of time. So at time t equal to 1, then we have S1, S of 1, S of 2. So here you observe that the output at any instant of time depends only on the input at that instant of time. So we'll talk about dynamic systems. So dynamic system. So this is a system whose output may depend on the past, the present, and future input at any given instant of time. So output so the output depends on the past, present, and future values of the inputs at any instant of time. So in other words, the system could be something like this: y of t, s of t, plus s of t minus 2. So at t equal to 0, we have s of 0 plus s of minus 2. So here you see, this is the present input, and this is the past input. So in other words, this is a delayed version of the signal, of the transmitted signal. And cases like this are experienced in a wireless communication environment where due to multi-part activities, some components of the signal arrives at a later time, should there be a direct component. Okay, so the other copies that arise at a later time are delayed copies of the signal. Then we have causal systems. So now this is a system whose output at the present instant of time depends only on the present and or better still, the past values of the input. So here, output depends on the present and past values of input. Okay? Now, take note that in causal systems, the output does not depend on the future input. So a causal system could be static and dynamic. Okay, it could be a static system or it could be a dynamic system, such that y of t, s of t, is the same as s of t, such that y of 0 is the same as s of 0, y of 1 is the same as s of 1, and then we say y of t is the same as s of t plus s of t minus 1. So that y of 0 is the same as s of 0 plus s of minus 1. Y of 1 is the same as s of 1 s of minus 2. So it means that at any given instant of time, the present output depends on the present input and past output. And you see that most of the practical systems we'll be dealing with are usually causal systems. Then non-causal system. In this case, the system whose output is determined at that instant of time depends on both the past, the present, and the future. So input. So in other words, the output depends also on the future input. So systems we described earlier, let's say y of t is equal to s of t plus s of t minus 1 plus s of t plus 1. So in this case, you see y of 0 is equal to s of 0, s of minus 1, s of 1. And so you see that this is the future input, okay? This is past, this is present input. So long the system depends on at least one future output, then it becomes non-causal. And then we have anti-causal systems. So these systems output depends only on the future values the input. Say y of t is the same as s of t plus 1. So y of 0 here is the same as s of 1. Y of 1 is the same as s of 2. So this is the future value of the input at this instant of time. And you see that non-causal systems could be anti-causal. And all, how do I put it now? Say all non-causal systems may not necessarily be anti-causal, largely because this is a non-causal system, but it is anti-causal. But should we have a present or past input present at that instant of time, given that input, then it may not be anti-causal, though non-causal. Then we have linear systems. So this is a system whose operation is based on the principle of superposition. Okay, principle of superposition. So in other words, it means it obeys two fundamental laws: the law of additivity and the law of homogeneity. Now, according to the law of additivity, should we have two separate systems? Say S1 of t goes into the system, and we get Y1 of t, and then we have a second system, S2 of t, and then that gives us Y2 of t. According to the law of additivity, should we transmit the sum of these two separate signals, S1 of t and S2 of t, and then derive an output that is equivalent to Y1 of t plus Y2 of t, then we will say the law of additivity applies, and then we can say this system is linear. Okay, and then for the law of homogeneity, should we have a system, say, with S of t transmitted through a system, and then where we get Y of t, and then should we apply this Y of t such that we multiply with a scaling parameter, then Y, let's say Y prime of t should be the same as Ks of t. And then should we transmit this system through a scaling parameter and then pass it through a system, then our Y of t should give us Ks of t. So should Y prime of t be the same as Y of t, then we will say the law of homogeneity applies, then we say the system is linear. Now, for a nonlinear system, we can as well conclude that the law, or better still, the principle of superposition does not hold. Okay. So time invariant systems. Now this is a system in which a time shift or a delay or advance in the input signal causes the same or equivalent time shift in the output. So meaning, should a signal be time delayed at the input, and then should we obtain an equivalent output delayed by the same time shift, then we say this system is time invariant. Means it does not depend on the time. And same, this is for delay, same for advance. So should we have this going through a system, then this, then we say it's time invariant system. So meaning a shift in time at the input at a given instant of time will result in an output with an equivalent time shift at that same instant of time. In other words, the time property or parameter cannot be scaled. Cannot be scaled. So should we get a scaled version of the signal, a time scaled version of the signal at the output, then we'll say it is time variant. Okay. So in other words, a time variant system is that system in which a time shift in the output, or in the input rather, of the signal does not necessarily result in the same time shift at the output. Then we now talk of stable systems. Now, when we talk about stable systems, we talk about bounded input, bounded output. So a system is said to be stable if the output is bounded for a given bounded input. So system is stable if the bounded output results from an equivalent bounded input at any given instance of time. So the idea of having bounded input, bounded output is that bounded input implies finite amplitude. Of the input signal, and bounded output implies finite amplitude of the output signal. So in other words, should we have a signal with a specific value of the amplitude, then we'll say this is a stable signal. How about an unstable system? It's a stable system, right? How about an unstable system? A stable system is a system that is not bounded input, bounded output bound. Okay, so this system is such that bounded input may not necessarily result in bounded output. An example is the ramp function R of t, which is the same thing as t of t. And see the output extends to infinity. So it is not bounded to a particular amplitude value, but rather just extends to infinity. So it is not a stable system. Okay. Okay, that's fine. Now let us go straight into the business of the day. Linear time invariant systems. Well, these models practical systems. Okay, so most of the systems we end up analyzing in practice models LTI systems. So, like we explained in our previous lecture, LTI systems are both linear and time invariant. They are both linear, and they are time invariant. So in other words, the principle of superposition applies, which is law of additivity, and law of homogeneity. And it's time invariant largely because the time shift at the input results in an equivalent time shift at the output. Say, okay. So hence, the LTI system is modeled such that there is an LTI system. We have T. I said this is H of T is the same as H of T convolving with S of T. So know that the continuous time systems are described by differential equations. We're going to come into that later. For most of the practical systems, we end up designing either in electrical engineering, for instance, using circuits and all of that. Say, let's assume we have a circuit with a capacitor, then we have a voltage source, and then let's say current I flows through this, I of T, and then this is C. So, and this is V of T, for instance. Then we can relate between these parameters using Kirchhoff's voltage law, and then come up with a system of equations. And then you see that the current and the voltage and the capacitor following from Kirchhoff's law, Ohm's law, is related by some differential equations. So in practice, continuous time systems, or better still, continuous time, linear time invariant systems, or continuous time systems in general are described using using differential equations. So, and then if continuous time systems are mathematically modeled using differential equations, then the general solution will therefore have a particular and a homogeneous component. Okay. So this leads us to the analysis of linear time invariant systems. So in order to analyze LTI systems, the solution, therefore, consists of two components. Okay? Now, since linear time invariant systems are both linear and time invariant, then it means that for the system to be linear, then the initial boundary conditions must be satisfied. That is, S of t, for instance, must be the same as y of t, so that S of 0, being the initial condition, must be the same as y of 0. Now, if S of 0 is not the same as y of 0, then we'll say this system is non-linear. Okay? So therefore, we'll have to analyze this system first by specifying the initial boundary values. And for us to do that, we'll have to investigate the zero input response. Okay? Now, I think it is worthy of note anyway to mention at this point that the zero input response is the output. This is the output. Let's write this. Of the system when the input is set to 0. So this is zero input response. Okay. Then afterwards, we therefore investigate the zero state response, which is ZSR. And this is the output of the system when an input is applied to the system. So it is the output of the system when an input is applied. So in other words, the general solution in terms of analyzing the LTI system therefore becomes the sum of the zero input response and the zero state response. Okay. So far, you will realize that the input and outputs are functions of time. Okay, so they're functions of time. But in practice, systems are easier to analyze when inputs and outputs are represented as functions of frequency. So we want to now figure out the system representation in the frequency domain for ease of analysis. Okay. Now, recall that we established in our previous lectures that a signal can be represented by the odd and even component, the even and odd component. making it a complex signal, right? A complex signal. So S of t is the same as cos t plus j sine t. And this is the same as ejt, where this epsilon jt is the Euler form. Okay. Now, you will observe that the complex signal consists of a real signal component and an imaginary signal component, such that the S-plane, therefore, becomes the plot of the imaginary component and the real component. This is the S-plane. Now you realize that the omega is in the imaginary axis, which is the same as 2 pi f, meaning the frequency component of the signal through the system is situated at the imaginary axis or components of the S-plane. Now, this information will be very necessary when we get to Fourier transforms. As we begin to discuss the convergence of Laplace transform to Fourier transform. Okay, this becomes very, very necessary when we begin to discuss the region of convergence. Okay, but not to worry. Let's not take it too fast. Okay, now that the signal S of t is the same as E j of t, then in the S-plane, S of t can be represented as EST. So, in a continuous time system, the function of time, let's not put it that way. The function epsilon st is referred to as the Eigenfunction. Okay. So the implication is that the function epsilon st is an input to the continuous time linear time invariant system, such that the output is a replica of this input, only that it is scaled by the parameter that defines the system. So in other words, ES of t becomes the input to the continuous time linear time invariant system, such that should this be defined by parameter h, then h est. Okay, where h is also a function of S, where H is the same as H of S. So now you'll observe that H of S is the coefficient and is a complex number whose value depends on the frequency S of the input signal. And once the input signal is multiplied by a complex number, the magnitude and the phase of that signal is altered. It changes. So this is very important because the parameter that now describes the system is a complex function. Okay? And once that complex function, which is H of S, multiplies the input signal, then the amplitude and the phase of this input signal changes. And then at this point, you should note that should the eigenfunction be multiplied by a unit step function, then it ceases to be an eigenfunction. So in other words, this is not an eigenfunction. It's not an eigenfunction of a continuous time linear time invariant system. Since u of t is a step function, the same frequency for the eigenfunction es of t to be an eigenfunction of a continuous time linear time invariant system, the same frequency must appear at the output for the eigenfunction inputs to the LTI system. Okay. So let us consider an example. So let us assume you have the eigenfunction. This is fed into a continuous time linear time invariant system, and then expected to get an output 1 over t epsilon t minus t over 2 t plus t over 2 s of tau d tau. Then you are expected to evaluate the eigenvalues corresponding to the eigenfunction. So since s of t is the same as the eigenfunction, then s of tau will be the same as es tau. And once we plug this into the output, that is y of t, will be the same as 1 over t integral t minus t of 2 t plus t over 2, which is the t, where t is the fundamental time period, then epsilon s tau d tau. Once we integrate this, so this is going to give us 1 over t. That's 1 over s. Once we integrate that, epsilon s tau t minus t over 2 t plus t over 2, where 1 over s is a constant, so we'll bring it out. That's 1 over st epsilon s tau st rather, right? t minus t over 2, t plus t over 2. So once we substitute the limits into the integration, so we have y of t to be the same as 1 over st epsilon st plus t over 2 minus epsilon st minus t over 2. Then this gives us 1 over st epsilon st epsilon st over 2 minus epsilon st epsilon st over 2. Then this will give us 1 over st. Okay, let's wipe this. We bring out common factor. St is common to both of them, so we bring it out. So that will be epsilon st over 2 minus epsilon st over 2 est. And now this is equivalent to this being the constant and this is the input, right? So say this is the same as lambda epsilon st, where the eigenvalues is given as 1 over st epsilon st over 2 minus epsilon minus st over 2. Okay. Now let us consider another example. Let's assume we have a circuit and we have a capacitor, it's a resistor, there's a voltage source, an independent voltage source, it's minus, then this is the voltage applied across the capacitor, plus minus, and there is this current I of t that flows through the circuit. So if we consider this circuit, and we already established earlier that continuous time systems are modeled using differential equations. Okay. So let us see how that goes. So in the first instance, if we apply Kirchhoff's voltage law here, so by KVL, see that negative Vs of t plus I of tr plus Vc of t is the same as 0. So I of t r plus Vc of t is the same as Vs of t. Let's say this is our first equation. But by Ohm's law, you know the current and the voltage relates here by I of t, same as C dV C of t dt. So this is our second equation. So if we put the second equation, put 2 into 1, what do we get? So I will be C R dV C dt plus Vc of t is the same as Vs of t. So now if Vs of t is our input, for instance, and Vc of t is our output, then I say this is 3, then 3 becomes, substituting this into this, Cr dy of t dt plus y of t is the same as s of t. That's simple. Now you see that given an RC circuit, that this is C, given an RC circuit, the system can be modeled using differential equation. And this is a first order differential equation. Okay. So alternatively, let's look at it the other way. So alternatively, if we switch the position of the input and output, if we integrate, let's integrate equation 2. So that's this equation. Then we're going to get I of tau d tau from negative infinity to t be the same as c integral negative infinity to t Vc of t dt. Okay, so this is going to give us negative infinity to t I of tau. The tau is the same as c Vc t. Okay, so from here we can say Vc of t is the same as 1 over c. If we divide through by c, integral to infinity t I tau tau. So if we have this as our fourth equation, so if this is our fifth equation, then this is our sixth equation. So if we plug in this sixth equation, let's say we put 6 into 1, what do we get? So I'm going to get I of tr plus 1 over c integral negative infinity t I of tau d tau is the same as Vs of t. Okay, so this is our sixth equation. So this time, let's say Vs of t is the input and I of t is the output. Then 6 becomes y of t r plus 1 over c infinity to t. Then I is y of t, which is now y of tau. The tau the same as s of t. So in this case, y of t, if we divide through by r, 1 over rc, integral negative infinity t, y of tau, d tau is the same as 1 over R S of t. Hence, should we differentiate through, then we have dy of t dt plus 1 over RC y of t is the same as 1 over R S of t dt. So once again, this is a first order differential equation. And now that we have arrived at differential equations for this circuit, then the solution follows directly, as we can actually derive the particular solution plus the homogeneous solution. Technically, what we're trying to drive at here is that all systems, regardless, whether electrical circuit systems, mechanical systems, petroleum systems, physical systems, whatsoever system it may be, so long it has the capacity to take in some input, process it, and provide an output, it can be described using differential equations. And that reminds me, while I was still in my doctoral research program, one of my professors told me at some point, said, you solve some differential equations, you're done. And trust me, the day we got through to solving the differential equations was the day I completed the doctoral research, okay? So, in essence, in modeling continuous time, linear time invariant systems, you must bear in mind that the system must be modeled such that the differential equations are used to represent or model the system. And then we could resolve it by solving for the zero impulse response and the zero state response to arrive at the solution in terms of analyzing the linear time invariant systems. Okay, let's look at one more example. So let's assume we have a circuit like this. And this is I of t, which is the independent current source, and ideal current source. We have the capacitor, Vc of t. So in this case, if we assume that S of t is the same as I of t, this is the input, and then Y of t is the same as Vc of t, then we want to determine the type of system this is. Is it a causal system? Is it a system with memory? Is it a memoryless system? Is it a stable system? Is it an unstable system? Is it a linear time invariant system? What kind of system is this? Well, the first thing is to characterize the system by developing its mathematical presentation. So, if we assume that C, the capacitor or capacitance of this circuit, is constant, then the output voltage across the capacitor and the current flowing through this capacitor can be related by y of t is the same as 1 over c, an integral negative infinity to t s of tau d tau. Okay, so from this output of the system, we can see that the output depends on the past and present inputs. Now, why that? Now, if you look at the limits of integration, you see that it ranges from negative infinity to some value at time t. It does not extend to positive infinity. Okay? So, the highest limit here is some value t. Let's say some value t, somewhere t, from negative infinity. So, in other words, we can take our limit of integration from some arbitrary values from negative infinity to some value t. And hence, it does not extend to positive infinity. So it means that this system can take on present and past values. Okay? So in other words, it means that this system has memory. And we know capacitors are storage elements. They store energy in the electric field. Okay, so it means this is a system with memory, meaning it is not a memoryless system. Okay, that's one. And also, you will notice that the output does not depend on future inputs. So meaning it is not a non-causal system. Since it depends on the past, let's change it to color. Since it depends on the past and on the present input, then it means it is also a causal system. So take note, it is a system with memory because it depends on both past and present input. And since it depends on past and present inputs, it is a causal system because it does not depend on future inputs. And then it means it's a realizable system because when we have causal and stable systems, we say they are practically realizable. Okay? Okay, let us check out for some other properties. So we have this, we have this. Now, let us test for linearity. Let's assume S of t. Let's change this. Let's assume S of t is the same as k1 S1 of t plus k2 S2 of t. S2 of t. Then y of t will be the same as 1 over c, coming from here, integral to infinity to t, s of t is that, k1 S1 of t plus K2 S2 of t tau S2 of tau K2 tau d tau. Okay. Then we're going to have to bring out k here. K1, 1 over c. So I also have something similar to this. S1 tau d tau is K2 and c integral to infinity to t S2 tau tau. You see that this now is the same as y of t is equal to K1 y 1 of t is K2 y1 of t. Now, given that s of t is this, and then we arrive at this, it means that the system obeys the law of additivity. So hence, it is a linear system. Okay, so it's the system is linear. Okay, now let us also consider another point here. So let us assume that y1 of t is the output produced after some time shifting in S such that we have S of t minus t sub k. So it means that y1 of t will be the same as 1 over c integral negative infinity to t S of tau minus tk. So now this will give us 1 over c negative infinity t minus tk. Should we then S of alpha gives us y of t minus tk. So meaning the system is time invariant. Time invariant. Now let us check for stability. So far we have seen that the system is linear, it is time invariant, so we can as well conclude at this point that this system is linear, is a continuous time, linear time invariant system. But is it achievable? Is it practical? Is it a realizable system? Let's check for stability then. Now, let us assume that S of t is the same as beta u of t. Okay? Note that beta is not the same as 0. Okay? So then, y of t will be the same as 1 over c integral negative infinity to t beta u of t u of tau rather d tau. And this is going to give us beta over c integral is infinity. Now, take note that since u of t is multiplied, let's assume this is t at this point. Now, u of t, this is let me use a different color. This is u of t. So it means that should it be that we had signals here, okay, whatsoever it may be. Now, by way of extension, once we multiply u of t by this signal, only t will exist. Only signals at this point will exist because this is u of t and this is y is s of t, right? So once that is done, then the limits changes. So it means that from negative infinity now reduces to 0, okay? From 0 now to t, okay? So that will be the time. And once again, this is t such that once the unit step function is integrated, like we said earlier in our lecture, we get a ramp function, tu of t, okay? Because here we are going to get beta of c into bracket t 0 to t. Now, so this is going to give us beta over c t. And t is the same as t times 1. And 1, where 1 is the same as u of t. Okay, so technically this becomes beta over c t u of t, which is equal to r of t. So hence, we have a ramp function r of t equal to u to t u of t. So meaning the system is unstable. Okay, because the output is not bounded, it extends to infinity. Okay, the output extends to infinity, so it's not bounded at the amplitude axis. Okay, I think this is a good place to stop for now. So far, we have been able to establish the background for the study. We've talked about signals, we've talked about types of signals, we've introduced systems, and we've talked about types of systems, and we've talked about eigenfunctions and the explain. And now we may have to go into analyzing systems in the explain. And this most likely, or definitely, not most likely, definitely leads us into transforms. Well, I hope this class was informative. Hope to see you some other time. Bye.